So this should be part 2 of our this example, of course. What we need to do now is to solve for the left side of section B dash C. So we're going to draw the free body diagram again of the whole structure. So we have here the free body diagram going like this. And then this is the area where we managed to cut, which is this section 2. So this is the cut area. We have here R sub A equivalent to 18 kilonewtons. And about 2 meters from A, we have 14 kilonewtons. Okay, this is 14 kilonewtons. And of course, this is the section where we have the shear force V sub B. Okay, let's assign that as V sub B because we are already here at section B dash C. And then we have the bending moment, okay, M sub B. And we don't know what is the length of this section, so that's why we need to assign that as X again. And in order for us to measure the perpendicular distance of this 14 kilonewton from this section is that we just need to consolidate the distances. Okay, this is 2 meters. So what is this distance? If this is the whole structure is equivalent to X, okay, the length is X, then we just need to subtract 2. Okay, so this is X minus 2, right? So it makes sense because this measurement is 2 and the whole measurement for this section is X. So we just need to subtract X by this 2 meters. We have this whole length. Okay. By applying again the summation of forces along the vertical. So positive going up, summation of forces along the y is equals to 0. So that should be 18 kilonewton. Then we have here negative 14 kilonewton and negative v sub b because it is acting downward. So those are the only forces that is acting on the y-axis or the vertical axis. So isolating v sub b, that should be 18 kilonewton minus 14 kilonewton. Simplifying everything, that should be v sub b is equals to 18 minus 14, basically 4 kilonewton. Then acting downward, since we have a positive answer, it means to say that our initial assumption for v sub b, or the shear force acting at that cross-sectional area, is correct. And the next step for this problem is to solve for the moment formula, bending moment formula for this section. Don't forget this is section B-C. So by applying again the summation of moments at this section where we cut the section B-C. So summation of moments counterclockwise is positive. Summation of moments is equals to 0. So we have here M sub B, which is positive. And what else is rotating? We have here 14 kilonewtons. This is the perpendicular distance, x minus 2. So it's going to rotate counterclockwise, so that is positive. 14, let's retain first the units, x minus 2. And last but not the least, we have 18 kilonewtons rotating clockwise, so that is negative 18 multiplied by x. And then we just need to isolate m sub b because this is the parameter that we need to solve by transposing everything to the other side and then rearranging. And about doing that, we just need to follow some algebraic mathematical operations. So m sub b is equals to, from positive, transpose negative. Negative 14 multiplied by x minus 2. Then this one negative transpose became positive 18x. So distribute 14 to the parentheses. That should be m sub b is equals to negative 14x and the positive 28 plus 18x. Simplifying again, that should be m sub b is equals to 18x minus 14x, that should be 4x, positive 4x, plus 28. So this is the bending moment formula for section B-C. Okay. And then the next one is, obviously, we are going to solve for section. Next is section C-D. Okay. So please bear in mind the forces for the shear force and the bending moment formula. Just going to erase this one. Okay, so let's proceed in solving for the left side of B-C. So our target for this case is section 3 for somewhere in between C to D. Okay, we're going to use the left side again. So let's construct the free body diagram. Okay, going like this. I'm just going to assume that this is correct. The measurements. Okay, this is the area where we managed to cut, which is this. Okay, and this one is we have 28 kilonewtons. Just going to retain the unit. And we have 14 kilonewtons, of course. And for this point, we have 18 kilonewtons. We're indicating the transverse loads. And then from this point to 14, this is A, we have a measurement of 2 meters. So that is 2. And from 14 kilonewton to 28, we have 3 meters. So this one is 3. Okay, this one is 3 meters. And for the whole section is measured as X, because we don't know what is the definite measurement. Okay, that's why we designated that as measurement X. And upon doing that, this portion, okay, from 28 to the area where we managed to cut that section, we just need to add 3 and 2 for us to get the difference between this whole length and this one. Okay, so that should be from that case, this one is X minus 5. Okay, so from A to 14 kilonewton, that is 2 meters, and from A all the way to 28 kilonewton, that is 3 meters, and from this portion of the beam where we managed to do the sectioning all the way to 28 kilonewton, that is X minus 5, because this whole length is equivalent to X and this whole length is equivalent to 5, so X minus 5. Okay, applying again the laws of equilibrium from this portion, this should be V sub C, and the bending moment at that section M sub C. So we need to solve for V sub C and then M sub C by applying the laws of statics. So summation of forces going up is positive. It should be F. Okay, this should be F sub Y is equals to 0. So we have 18 going up, so positive. We have negative 14 because it is acting downward. We have negative 28 because it's always acting downward, that's transverse loads. And we have negative V sub C because that is the shear force acting at this section. Okay, so simplifying everything by transposition, V sub C is equivalent to 18 minus 14 minus 28. That should be negative 24 kilonewtons. This is just a simplification. So this should be negative 24 kilonewtons. So this is the shear force at this section. And the next step is for us to solve for the bending moment. So summation of moments at this section where we managed to cut the beam. So again, counterclockwise is positive, summation of moments is equals to 0. So that should be positive M sub C. And this 28 kilonewtons rotates counterclockwise, so that is positive 28 multiplied by x minus 5. Let's retain first the unit, so to avoid confusion, we have 14 kilonewtons rotating counterclockwise, so that should be positive 14 multiplied by what is the perpendicular distance. So this whole length is x, this length is 2, so means to say that this length is x minus 2, so x minus 2. And last but not the least, we have 18 rotating counterclockwise, so that should be negative 18 multiplied by the perpendicular distance equivalent to x. And then we just need to simplify everything. So we have here m sub c is equals to, it's all about algebra, transposition. This one, negative 18x, becomes positive 18x. This one becomes negative 28 multiplied by x minus 5. Then also this one becomes negative 14 x minus 2. This is just simple algebra. From this point, m sub c is equals to 18x. Distribute negative 28 to this polynomial. So that should be negative 28x plus, what is 28 multiplied by 5? That should be 140. So positive 140, because negative multiplied by negative is positive, minus 14x, and plus 28, because negative 14 multiplied by negative 2 is positive. Negative is positive. Then further simplification, m sub c is equals to, we have 18x minus 28x, and then we have negative 14x. So that should be negative 24x. Okay. Negative 24x, and then we have 140 plus 28, so positive 168. So this is now the bending formula for section C-D. Okay. So after this point, we just need to use some substitution.